Hello everyone. In this video we are going to talk about a recurrent neural network that is a little bit more sophisticated than the Elman one that you saw last time, and this is called long short-term memory, or LSTM, which can help with the vanishing gradient problem that I mentioned we have in the Elman network. Remember when we talked about the back propagation through time, I told you that you are multiplying all of these partial derivatives together, and when that happens, it means that if they are small over time, all of these smaller than one numbers multiplied together will converge to a very, very small number close to zero, and that means no learning can happen. So is there an alternative to it? Is there something that can help with? The answer is yes, and one such solution is called LSTM. So what is it? Let's take a look. By the way, I need to mention that some of the material here are basically borrowed from Wikipedia. So here we don't have, remember in the Elman network, all we had was the input X, the hidden state H, and the output, which you call it Y. In this case we call it O, but doesn't matter really, so either Y or O, and that was it. Here you have more. Here you have 5 variables, and basically you have or you might call 6 basically, because this Y is for the entire network. This is just one unit. So this is not the entire network, this is just the LSTM unit. In a unit of the simple recurrent network, you did not have the outputs, you only had X and H. And H of t was a function of H of t minus 1 and X of t, remember that? So that's all we had. And now we have more. As I said, we have 5 variables or vectors involved, or states. One of them is called the forget gate, one of them is called the input gate, one of them is called the output gate. And the good thing is this F, I, and O are the first letters for forget, input, output. We have a cell state, which again starts with C, and we have the hidden state H. So these first letters and these letters used for the notation are really good, and it's not my notation, it's a common notation in LSTM. And I'll explain what these are. Here we are using the sigmoid function. This sigma is the sigmoid function really. Okay, so this activation function for F, I, and O, this is the sigmoid function. And we have 2 other functions which we use for cell state and hidden state, and one of them is this guy, f of t, and the other one is f of h, and typically they are the tangent hyperbolic function. Okay, so these are what? These are the 2 types of, or 3 types of functions we have, and the 5 states. Now what is it? Let's explain them through the equations and through this diagram. This diagram again is borrowed from Wikipedia. I just added a few extra things to it and made it a little bit more readable compared to what is over there. So what do we have? Let's take a look. So we have a variable or a vector called forget gate, and you see this is a simple recurrent neural network as we saw in the past. You see, it depends on h of previous time and x of t multiplied by their own weights and a bias passing through a sigmoid function. So this is a sigmoid function, not a hyperbolic, as opposed to RNNs, right? Or you might just call it like a simple, basically dense layer. You might call it like that, okay? Because the sigma is tangent hyperbolic, and this is sigmoid, so you might say this is a simple dense layer, and that they use you for, let's say, classification, for binary classification. So the output of this f is definitely between 0 and 1, right? Because it's a sigmoid function. And so if this f is 0, you'll see down here in this equation for cell state, if f is 0, when this f is multiplied by c of t minus 1, it makes this term go to 0 okay, but this term might stay. So what does that mean? It means the previous cell has no effect on the current cell. So you decide to forget the previous cell value, okay? But if it's 1, you decide to keep the previous cell value. And what's the use of a cell value? Well, you'll see that the cell value is passed to your f function and then multiplied by the output gate to get the output. Okay? Yes? Because the output of this LSTM unit is really h of t. The c of t is really typically not sent out. This is typically, basically, if you see it in Simulink, right? It is terminated, and we typically ignore it. We typically hide. We don't need this c to come out of the LSTM. We need this h to pass to the next layer, which is like a dense layer or something. So this guy goes to the next layer. Okay, this is just an internal state, this c, and we don't need to send it out. Okay, so we pass it to this hyperbolic function f of h multiplied by this other o and send it out. So this c is important. Okay, this is, as I said, an internal state which we call cell state. Now, let's go back here, look at these equations again. So this symbol that you see here, this is the element-wise product. Some people call it the Hadamard product, okay? So this is an element-wise product between f and ct minus 1. So again, ft of 0 means forget the previous state, ft close to 1 means keep it, okay, for calculation of c. And input gate here is what? Input gate is, again, a very similar calculation like f, using sigmoid function and, again, its own weight and its own biases. Using the previous input and the previous hidden state, you get an input gate. Now, what's the job of the input gate? Well, if you look at where the input gate is used, you see input gate is controlling what? Controlling the value coming out of this hyperbolic function f of c, which is based on the previous input and previous hidden value, and from a tangent hyperbolic function. And if this I is 0, then this guy here will not affect the current c of t. If it's 1, then this guy is going to affect what? Entirely this c of t. So you see c of t is what? C of t is a combination of, c of t is a combination of two things. Previous of its own and the value from this tangent hyperbolic, which is coming from input and the previous output of the layer. Okay? It's a combination of them, and the weights for this combination are f of t and what? I of t. Okay, so you have two gates, you have two weights that you can change, and they decide how much of the history and how much of the internal history, internal memory, and how much of the effect by the inputs to the system and the previous outputs to basically keep, right? And then remember, this c is not going to be sent out. This c is going to be passed to the hyperbolic function f of h, and it's going to be sent out if this O of t, this output gate, is close to 1 again. Because this O of t is, again, coming from another sigmoid function, so this O of t is also between 0 and 1, as well as I of t. All these three variables are coming from sigmoid functions, so they're all between 0 and 1. So if this O is also a big number close to 1, it means this LSTM unit will send out this value of this hyperbolic. If it's 0, means, hey, don't send anything out. Okay, suppress, damp the output. So you see you have three gates. How much of the input to use? how much of the previous state or previous memory to use, and whether in the calculations inside this unit should be sent out or it should be kept. Okay, these are the forget gate, input gate, and output. You have three switches. You have three switches. So if you want, if you look at this diagram, you can see it better. It's like, look here, x of t and h of t are going through a sigmoid function and creating f of t. So what happens here is this h of t minus 1 is multiplied by what? By whf. So here this is multiplied by whf, and this x of t is multiplied by wxf here, added a bf to it, passed through sigma to get f of t, and then f of t is dot multiplied. This product here is the same as that circle, by ct minus 1. So you'll get what? You'll get this term here. Then it is added to, so this is f of t, as you can see, c of t minus 1. It is added to now this term, which is I of t multiplied by this guy, and this guy here is this f of c here, added together. So what comes out here is clearly what? C of t. So that is this branch here, and this one are showing C of t. Now, in order for this C of t, which we don't need to really send out, but in order for this to be generated, we have two switches. So one switch is I of t, so I can here show you that this I of t is like a switch. And also this other switch here, f of t. And this switch is not like a perfect binary switch. That's the problem. This I and f are not perfectly binary switch. What they are a fuzzy switch, basically. They can be closed, they can be open, they can be half open. So some people, instead of using the idea of switch, they use the idea of a sliding door or a sliding gate. So they say, hey, this is like a gate here, and a portion of this gate can be what? Open, or all of it could be open, or all of it could be what? Closed. Okay, and similarly for I. So this I, F, and O are like fuzzy gates that can be partially open, or closed. So that is that part. And then these other functions, you can see this is the path for I of t. This path here is for O of t. And finally, when you create O of t, it is multiplied by fh. You pass this C of t to fh. And finally, you get the output h, which can go to the next layer, okay? Or it can go to anywhere else. So it can go to the next layer, it can be fed back to somewhere else, okay? So you just really need one of these h. So here that means an extra feedback, basically. And here it means pass over. So there is no branching here, okay? There is no branching, it's just one signal passing over another signal. So this is what this guy does. And since it can remember previous history, previous memory, up to so many thousands of time steps, we can call it a long short-term memory. How can it remember a lot of previous steps? By keeping this f of t alive. Okay, if we keep this f of t close to 1, it is going to remember all of these previous cell values, and so they will affect the c of t, and c of t will affect h of t if, of course, this O of t is also open. Okay, yes? So let me just read through this for you. Although I explained all of them, but just one more time. The cell remembers values over arbitrary time interval. There are 3 gates to control information into it, inside of it, and outside. The forget gate decides which information to discard from previous state by assigning a value to it, and between 0 to 1 from the sigmoid function. The input gate decides which piece of new information to store in the current state. And again, the new information is what? The new information is actually this x of t. Okay? And the output gate will decide basically how much of that goes to output, as you can see over here. So this is an LSTM, and it is more sophisticated, and it can perform better than a simple recurrent neural network. And so to demonstrate that for you, here I have my LSTM code, which is very, very similar to the Elman network. And here again, I'm gonna run it on the Yahoo Finance values, the stock market that we had last time. And remember, this is the data for S&P 500 in so many days of 2023. And here we use only 10 data points to predict the 11th data point, basically. And we formatted the data. Everything is like last time. The only difference is last time this guy was simple RNN. This time it's called LSTM. And again, all you need to pass is the number of units. Everything else is the same. Then you pass it to the compile. You use the Adam, a learning rate, the loss function still MSE. And let me tell you a few other things before we go to training the model. As I said, the 2 functions fc and fh are tangent hyperbolic by default. And one thing in TensorFlow Keras that you have to pay attention, you cannot select them different from each other. So although in general they are written like they can be arbitrary function, right? If you look here, this ft and fh, fc, and because ft is the forget state, fc, this guy, and fh, this one, these two are written like you can use any function that you want. But if you look at Wikipedia's picture, these two are just replaced by tangent hyperbolic, which is the default. Now, it doesn't mean you can't select any other function for them. You can even write your own function. You can use something called PEEP LSTM and so on. But pay attention that in Keras, if you make this fc another function, whatever it is, the fh should also be that same equal to fc. Okay, so fc should be equal to fh, otherwise it's not going to work. And another thing is, if you write your own function or use any function other than tangent hyperbolic for fc and fh, then guess what? You cannot use GPU. So GPU can only be used if you choose fc and fh to be tangent hyperbolic. So be careful about what you choose for them. Another thing is, remember I said the only thing coming out of LSTM unit is H, the hidden state. But can you get some other things out of it? For instance, can you get the C out of it, or O, or anything else? Yes. All you want to do is, after this LSTM say, hey, return state equals true. Then it will return O and C for you, and C is that one that we didn't want, but you can get it out. Or the H that it gives you is the current H, H of T. Could you get previous H's out of it as well? Yes. Again, what you need is, you can say return sequence equals true. Then it returns all of the previous H's for you to all of the sequence of H. Okay, so these are some extra options if you want. But here, for our basically goal, we don't really need to do that. One other thing I did here is, instead of splitting the data into half and half, which I did last time, half training, half testing, I used the rule of 70%, 30% that I mentioned to you in the past. So I used 70% of the data for my training, as you can see, and then I used the last 30% of the data for what? For validation. And I use 100 epochs. So the more data you have, the better your chance for prediction. But again, we'll talk about whether you can really predict the stock market or not. But here I'm using 70%, 30%. I'm using 10 units and again 10 data for predicting the 11th data. Everything else is almost the same learning index and function. So we trained the network, which I did for you ahead of time, and then we plot for you the loss function, both on training set and testing set, and you see it did actually a very good job. Okay, the testing set is not going up, and it went down and almost plateaued. So here I tried several different options for T for the number of neurons, and there is no general magic formula to tell you exactly how many neurons to choose, how many epochs to choose, what learning rate to choose. And I mean, you can schedule the learning rate, which is a good idea, but in general, many of these hyperparameters are under your control. How many data to use for the next data point and so on. So I tried a bunch of different things, and it gave me finally this good run. And now if I do the one-step prediction, okay, so this is really the one-step prediction, okay, and here if you run that, you see that the one-step prediction of this network is not bad actually. It's relatively good. It is capturing almost everything. But is that really good in terms of real world? Well, one step ahead means 1 day ahead. So if you want to buy your stock market today and sell it tomorrow, maybe it is doing a good job, but in reality, that's not how you get any good money out of the market. Because if you buy it today and sell it tomorrow, the changes are very small. You gain from the market if you leave it for some time, okay, at least a month or something like that. And that means you need to do multi-step prediction. So here we try to do multi-step prediction, which I showed you in the previous video, which assume that you don't have the remaining 30% data at all at the end. And so you try to predict the data at the 71th row and then 71st row and then 72nd row and third row, using replacement of values you have with these new predictions. So you get accumulated error, and guess what? Look at what you get. Right? Complete, I would say, unreliable learning, right? It just tries to do a little bit good in the first one, but after that, the accumulation error is completely ruining that. And of course, you can get all the weights and everything. Look at the model summary. But multi-step ahead prediction for a stock market using just the history of data and even this more fancy LSTM is not possible. And you might say, why? These LSTMs are networks that you use in lots of different applications. You use them in natural language processing, you use them in robotics controls, you use them for lots of different things. And they have been shown to be very useful. So what happens to the stock market? Right? Why can't I predict anything in the stock market with them other than just one step ahead? And the reason is here, when you just look at the history of the data, and this X that you pass in, remember, what is this X that you're passing in this case? This X that you're passing is simply the history of the data. So if you look at it in terms of a dynamic system, you say that, hey, this is this system that I have, and this is this future stock market values, and all I need is to look at what? Previous stock market value. That's basically what you're doing. You're training a network from previous values, and how many? Actually just 10 in this case. 10 current and maybe just one future value. It was not bad, but now if instead of 1 I want to change it to what? Maybe 5. So I look at 10 previous days and predict 5 future days, or even 2 future days, or 3 future days. Then my LSTM is only depending on this 10 previous data. Is that really the case in real life? Absolutely not. Well, what about all these other factors in real life that come in and determine the value of the market? I mean, it's not just the previous data. Any decision made by big stockholders can do anything, right? So political decisions, market decisions, customer decisions, Corona, all these other things, some big investors manipulating the market and so on, they all will affect these numbers, right? Some wars unpredicted, everything. There are so many factors from the real world coming in, and you're not just looking at any of them and you assume that, hey, with just this fancy set of 5 variables and some switches and so on, I'm gonna get the job done. No, you can't, unless you consider all of this too, and you have a way to find some of them, because many of them you cannot even predict. Okay, so for future, when you want to see in 2 days, maybe for tomorrow, yes, you know what is going on today, but in 5 days from now, you need to know the future 4 days, whatever happens in the world. Do you know them ahead of time? Absolutely not. So all of these factors that you're ignoring are going to make that future predictions impossible. Okay, it is going to make it impossible, especially these stock markets are like real time. Okay, any change in the world in real time will affect them. So you have to be really updated about everything in real time, and you have to have a very, very complicated model to properly weight them and then predict that. So whoever think that with one LSTM they can get the markets predicted and become a millionaire overnight, that is not going to happen. Okay, so hopefully this video showed you something about LSTMs, and again, they have lots of applications. In one of my future videos I'll try to show you another application of them where they perform better than stock market. Okay, so you don't think that they are useless. They are absolutely useful, but you have to have a lot more for stock market. So thank you so much. I'll see you in the next video.